distributions on Riemannian symmetric spaces in the large N limit. And first of all, so hey, I'm Simon. I'm a first-year PhD student here at the University of Cambridge in theoretical physics and applied mathematics. But this project kind of came up as a summer research project last year in the engineering department at the University of Cambridge as well. And I worked in collaboration with Cyrus, Mostajeran, and Salem on this project. Okay, so before jumping in, maybe so I would like to emphasize that kind of this project is very nice in the sense of bringing different topics together, and I hope to convince you today that this kind of bridges some nice aspects of random matrix theory, data analysis on manifolds, and also theoretical physics. Okay, let's go ahead. So here, before going into the details, I would like to start with some motivation. So in the context of EEG-based brain-computer interface, one usually considers data from n electrodes, which are attached to a subject's head, and then one measures kind of data from n electrodes at t time points, t discrete time points, which gives you an n by t matrix, which is of course way too big a priori. So as the signal descriptor, one usually considers then the associated empirical covariance matrix, basically x times x transposed. And it's not hard to see that this matrix here is kind of symmetric and positive definite. So this lives in not in any vector space, in any high dimensional vector space, but this potentially lives in a high dimensional Riemannian manifold, which is the manifold of SPD matrices. And today I'm mostly going to consider this space of this manifold of SPD matrices, which also comes up in many other applications. Okay, so why is this kind of, what can we do with it, or what would we like to do with it? In general, one would like that kind of in a case where we are given L samples, so points on this manifold which might come from L sessions on the same subject, we would like to estimate some parameters of some distribution obeyed by these samples. And then it's also again natural to assume that the distribution is a Gaussian distribution, and then this basically reduces to parameter estimation of x bar and sigma. Okay, so I mean, we are speaking about a Riemannian manifold here, so it's not a priori super clear what the right Riemannian what the right Gaussian is, but in our case, let us consider this the definition of the Gaussian to be this here. So if we are given some Riemannian manifold, we basically just write down the normal thing we know from Euclidean space, but just instead of the Euclidean metric, we take this Riemannian distance function, and then we have to normalize. Obviously, we have to restrict to manifolds where this makes where this expression makes sense, in the sense that this normalization factor has to be finite. Okay, so in a general non-homogeneous manifold, this we might run into some difficulties. Namely, first difficulty in handling such a distribution would be that kind of this normalization factor might depend on the parameter x bar, in which case it would get very messy and very kind of intractable. So that would be kind of in a highly nonlinear case. You would not expect to be able to compute this normalization factor, because you would have to kind of evaluate it at every point. Anyway, kind of we are in the lucky situation that the space we were considering, the space of SPD matrices, is a nice and symmetric space. So kind of basically every point looks the same. So I mean, and this is in general true for any so-called Riemannian symmetric space, which is usually known to be written as a quotient of 2D groups. So I mean, okay, basically what you can think about is a manifold on which every point locally looks the same. This is not the rigorous definition, but there's a nice theory developed in many books, and I don't want to go into the details here. But yeah, basically, so the space of SPD matrices is definitely a homogeneous symmetric manifold. And on this manifold, what is intuitively clear, but kind of what one can also show, is that this normalization factor does not depend on this parameter x bar. It only depends on the sigma. But still, it is not a priori quite clear how to evaluate this integral even for sigma. I mean, if we are considering, say, many electrodes in our example, the space M would still have a very large dimension. And as this dimension of M gets large, it's still probably in general quite hard to evaluate this integral over this nonlinear space. But again, anyway, we are quite lucky, and it turns out that this integral can be simplified in a way that makes it accessible to some random matrix theory techniques and theoretical physics techniques. And this is what I would like to go into now. Okay, again, kind of mostly focusing, going back from the general case of a general manifold back to our case of interest, the space of symmetric positive definite matrices, or some kind of complexified version of it, or some quaternion version of it. So this is just kind of a bit more general, but it's random matrix theory. In random matrix theory, this notation is fairly known, but I will just adopt it here. So for the real case, we define parameter beta to be equal to 1. For the complex case, we define it to be 2. For the quaternionic case, we define it to be 4. But so this doesn't matter too much. What we have at the end of the day is that this normalization factor turns out to be, after kind of some calculation in local coordinates, in some sort of polar coordinates, this localization factor turns out to be basically some constant times an integral over this Vandermonde determinant part in some, where we also have in the integration measure some weird potential here, which looks potentially very unfamiliar and which is a bit non-standard. But at the end of the day, it boils down to this kind of nice integral over the Vandermonde determinant. And if you're from random matrix theory, you will realize that this is kind of something which is fairly familiar in the random matrix theory literature. Namely, it's a random matrix ensemble, but we don't have the standard potential. We don't have a known standard potential here. We have this weird log squared potential. And I mean, if we had a standard, I mean, if we would like to, if we would think about the standard Gaussian unitary, Gaussian orthogonal, or Gaussian symplectic ensembles, we would consider it just a squared potential, but we have this kind of different potential here. But anyway, this is already kind of a nice structural insight that our normalization factors, which just started their life as hard integrals, kind of have this structure that also appears in random matrix theory. Okay, and then, I mean, even better so, it turns out that this integral is kind of, even though this potential is kind of non-standard, this integral has been studied in the case beta equals to 2. So just in the complex case, this is even a very kind of famous, function, or a famous integral appearing in the physics literature. Namely, it appears as the partition function of UN Chern-Simons theory on S3. And this is also kind of, I don't want to explain what Chern-Simons theory is, but this is kind of a nice bridge to the theoretical physics literature here. And again, this then can be pretty much solved, has been fully solved in the physics literature as well, using Stieltjes-Wiegert polynomials, and I will briefly explain this later. But kind of the case beta equals to 2 is fully solved. You can write down an explicit formula for the integral, but still beta equals 1 is very hard, and we have no idea how to go forward with it. Also, there are much more kind of interpretations on what this integral is. There's a statistical physics interpretation, which is sometimes known as the Coulomb-Gas approach or formalism in the random matrix theory literature. Also, recently there has been papers by Sartelli and Thiers, which claim that this is related to vicious random walkers, which is very interesting. And there's much more, but I don't want to go into that. But maybe kind of I want to elaborate a bit more, just to drop a few buzzwords here. I want to elaborate a bit more on the relation to the physics literature. So I mean, in general, these normalization factors also, for more general B, they appear as kind of partition functions of certain gauge theories. So this is just one slide. I'm gonna note this real quick. And it is a general topic in the physics literature to kind of expand such partition functions in terms of Feynman diagrams. And in this case, I mean, physically speaking, as the theory turns out to be a gauge theory, one has this kind of weird Feynman fat Feynman diagrams and planar Feynman diagrams, and then it is kind of natural to write down a pictorial expansion of the function Z. This is something which I don't want to explain here in detail, but it is very well known in the physics literature that one can basically build up an asymptotic expansion by just kind of taking such propagators, gluing them together with vertices. I mean, in our case, we would have much more vertices, but I don't. It's just a very schematic description here anyway. And then one can glue them together in this way to get different such graphs, and some of them can be embedded into the sphere. These are the so-called planar Feynman diagrams, because one can draw them on a plane basically, while others might potentially not be able to be embedded into a sphere, such as this example here. But to make it short, in the physics literature, it turns out that there's an interesting limit, namely the so-called large N limit or planar limit, where only these planar diagrams will contribute. And why am I saying this? Well, basically, this well-studied limit from the physics literature, this large N limit, turns out to be super interesting, and exactly the limit we are actually interested in here for us. Namely, it's the limit where kind of we would have larger and larger matrices. So our SPD matrices get larger and larger, which is the case which is a priori hard to track numerically. So say like considering a lot of electrodes rather than like considering thousands of electrodes rather than just 10. So yeah, I mean before people tried to compute this, and it was kind of n equals 20 was the kind of largest case. But here we would like to consider this large N limit here. And okay, so it turns out that one can then, motivated by this kind of physics story, play this game and find out a lot of interesting things on how to compute the large N limit of these partition functions, in particular of Z1. And so here's the first way how to do it. So the first way how to compute the partition function of the large how to compute the large N limit of this Z1 is that basically one can realize that there's a certain scaling argument. So I won't go into the details here as well, but I just want to show the result real quick and skip the boring calculations in a sense. But basically, it turns out that the difference that betas are related to each other in the large N limit. So that it turns out that kind of this case of interest here on the left hand side, that beta for any beta, potentially you can plug in beta equals to 1. It's just related basically in the large N limit. It's the same as the partition function of Z2 and some kind of factors which are easy to compute. And then we would like to use that, as I already mentioned before, Z2 is explicitly known. This is the lemma here, and the fact that there are kind of well-known orthogonal polynomials and ways to compute Z2 at finite N even. So this is one way on giving a concrete explicit formula for this large N limit of Z1, for example, if you plug in beta equals 1 here. There's another way on how to do this a bit more directly, which is related to the asymptotic eigenvalue distribution. So if you might have seen in the standard in the more kind of in the more well-known examples of random matrix theory ensembles, that there's kind of this Wigner semicircle law, which gives information about the asymptotic eigenvalue distribution. And it turns out that kind of a similar thing can be done here as well. And in our case, and instead of a semicircle law, we just get this kind of a bit more exotic looking asymptotic eigenvalue distribution. And this gives us the fact that we can up to some prefactors which I absorbed here into the Z. We can compute the large N limit by some kind of universal, also universal in beta universal function, which depends on this eigenvalue distribution here, for which we have kind of concrete formulas. So this can be explicitly written down in this way as well. So yeah, this gives kind of two nice ways on how to compute this large N limit of the logarithm of the partition function, or the normalization factor as we call it. Okay, so let me summarize and briefly give some outlook as well. I mean, so maybe first of all, what did we do? We did manage to compute this kind of limit where we have many dimensions, so that the high dimensional limit of this normalization factor function, which was a priori just very hard to compute, and we did not know how to get a handle on it. And then kind of so we computed a large N limit of it. But still, at the end of the day, so the first big question we would have is kind of at the end of the day, when we plug in some data, we are not in the n is equal to infinity limit. We are at finite n, and we did not take kind of finite n corrections into account. So it's kind of a question how how good this approximation by the large n limit would be in concrete cases. That's something we plan to experiment a bit more with and yeah, speak about more in future work. And then also, I mean, if one would not like to bother trying to just approximate by the large n limit, it would also be interesting to kind of compute Z1 to all orders in 1 over n. So just compute it exactly and take all the finite n corrections into account. This is harder, and one would need to compute so-called skew orthogonal polynomials for our weight potential, which is so far apparently not known in the literature. But I would be happy for any comments on this if people know know something like this by chance. Any random matrix theory people. But yeah, and then of course it would be kind of nice as well to make contact with actual applications and apply everything to brain data with, of course, then with many senses, which would be possible. Okay, on the theory side of things, there's also much more to say. So we kind of, I was just speaking about SPD matrices today, but we did all of it as well for the so-called Siegel domain, which is related to many interesting applications involving block-Toeplitz matrices. In this case, we did not quite find explicit calculations yet, but we are kind of almost there as well. We found a nice saddle point equation, but yeah, one would have to solve this equation to get an explicit asymptotic eigenvalue distribution and so on. So there's some open work on the Siegel domain as well, but this is kind of commented on in our paper as well. But yeah, moreover, there are much more kind of symmetric spaces that are out there to be understood, and it would be really nice to kind of understand more symmetric spaces and compute more partition functions of, yeah, say other symmetric spaces than SPD matrices and the Siegel domain. And also, I mean, there are kind of some very exciting things which go out relating also kind of compact symmetric spaces to non-compact symmetric spaces. I mean, I was just speaking about non-compact symmetric spaces so far, but obviously, I mean, it is known in differential geometry that there's always a compact dual to any non-compact symmetric space, and it would be quite nice to kind of understand the relation of compact and non-compact spaces in terms of these normalization factors. And yeah, we already successfully did that in our case of the complexified in the case of complexified SPD matrices, but would be nice to look at other cases. Okay, thank you. And if you have other questions, I hope we can get some discussion going. Yeah.
I'm sorry, the room is mute. I can't hear the rest of the room. There it is. Now it's working.
Is it working now? Okay. So I have maybe one question, which is probably a very difficult question. So the theory, there's very nice link between the computation of the normalization factor here and the theory of random matrices. But it's working apparently only for symmetric spaces. So for non-symmetric spaces, we know that there is gradient of the curvature. Do you have a feeling or any idea of how we can at least approximate the first order of what would be the impact on the repartition function?
That's a very good question. Thank you. Yeah, I'm afraid our I'm afraid our techniques like heavily relied on having some sort of Lie group description. So I'm not. I mean, so it's a very good question, but to be honest, I feel like I don't have anything too useful to say about it.
That was I said from the beginning. It's not a nice question, and it's definitely not a question for which I have the beginning of an answer. So it's just if there is an intuition, but
I mean, yeah. So I can tell you a few problems why. Okay, maybe some intuition why it's not expected to work. So first one is probably that there's like no nice Lie groups involved that we can use, and another thing which would definitely make it more difficult is that the normalization factor will depend on the mean as well, probably.
Yeah.
So one would kind of, I mean,